All right, today we're going to talk about the atom. If you look at the periodic table hanging on the wall by the door or the one that you've been handed in front of you, those are all different elements or different atoms. All right, that is the foundation of all of chemistry. Everything in the world, everything that we know to exist is made up of some combination of those 118 elements. All right, pretty cool, right? So today, what we're going to be talking about is what is the atom and how can we take what they give us on the periodic table, the mass number and the atomic number, and be able to determine the protons, neutrons, and electrons and understand the atom structure. All right, very foundational information today, but very important as we move into further units in chemistry. You must understand today as we move forward. So, what is an atom? That is the smallest particle of an element, and that atom holds everything that gives an element its properties. All right, so the properties are held within that atom based on the number of protons, electrons, how it's going to combine with other atoms and other elements. So an atom is that smallest part. So when we look at the properties of an atom, these are the little blanks there and bullet points on your guided notes. All right, it's going to be spherically shaped. It's a round ball-looking shape. Positively charged nucleus. All right, so our nucleus is right here on the inside, and so positive charge on the inside. That nucleus is composed of protons and neutrons. All right, neutrons. What does neutron sound like? Sounds like neutral, right? So in here in our little nucleus, there's also some neutral particles. And then protons, think P for positive, or look, this T right here looks like a little plus sign, right? So that reminds you that protons are positive. So I've got nothing but neutrality and positivity on the inside of my nucleus. That's what makes that nucleus positively charged, all right? Because there's nothing that exists except for neutral and positive on the inside. So 99.97 of your mass comes from the nucleus. That's where all the mass is made up of. So your neutrons and your protons have some mass to them. And then when we look on the outside, you've got your electrons flying around. All right, they're floating around in the electron cloud. They're moving constantly. If we know that 99% of the mass comes from the inside right here at our nucleus, what does that tell us about these electrons? They're very, 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 very tiny, all right? So what we're going to look at here on the next slide is the weight of an electron is so small, we don't even count it, all right? So all of that mass comes from right here on the inside. So you've got negative charge on the outside. Those are our electrons, and then neutral and positive in your nucleus. So let's take a second. I'm going to give you a second to write down this table in your notes, and then we'll talk about it. All right, now that you have that written down, let's take a look. Proton, we can abbreviate it with just a P or a P plus. That just reminds you that it's positive. Pretty simple, right? We're not going complicated with these symbols. Neutron, just the N with that little zero lets you know, hey, there's zero charge here. It's neither positive nor negative. If I looked at somebody in the classroom, I said, they're pretty neutral, right? They're not positive, they're not negative, they're just kind of hanging there in the middle. Electrons can be E or E minus. That little minus sign reminds you that it's negative. All right, so real simple on those symbols. Where are they located? We know that our protons and neutrons stay together inside of the nucleus. That, because they have a positive and a neutral charge, means that our nucleus, as we just looked at last slide, is going to be positively charged. All right, and then you have electrons that fly around on the outside. All right, so somebody yesterday asked a really good question. How are the electrons staying around the outside? Like, wouldn't gravity pull them down? Why do they all stay together in an atom? All right, the reason being, what do we know about opposites, right? You've got a positive and a negative, and we say that opposites do what? Opposites attract. So you have this positive core, and you have all these negative electrons that are flying around. That positive has a pull on these electrons. So these electrons and the positive core are attracted to each other, and they have a core. And so as we'll talk as we get later into the units, they end up farther and farther away the more electrons you have, because you have so much negativity to try and pull in. So it's a really good question somebody had, in case any of you were wondering, why do those electrons stay there? That's essentially why. There is that attraction between your positive charge and your negative charge that is pulling that atom together and holding it together. All right, and then lastly, when we look at mass here, with the mass, notice the only thing that has a mass is your proton and neutron. AMU stands for atomic mass unit. Atomic mass unit. Obviously, we would not want to measure a proton in grams, right? We wouldn't take it to the back of the classroom and put it on a scale, because it wouldn't even show up. All right, so they measure the mass of atomic particles and atomic mass units. So 1 AMU, proton and neutron both weigh 1, but if we look at electron, it's 1/2000th of an atomic mass unit. 1/2000th. Think about that. If I were to go back on the scale and put something on the scale and I said it was 1/2000th of a gram, right? That would be like super, super, super small. So now we're talking about atomic mass units, which are already small within themselves, and now I only have 1/2000th of that. So that is why we say it is essentially zero. All right, electrons have no mass. So imagine I take you and I sit you on a scale, and I take your weight, right? And then I hand you a feather. Is that feather going to change your weight? No. All right, so that's essentially what the electron does to the atom. I've already got the mass from the protons and neutrons. If I set them on a balance and took the mass, I would get a mass. But if I all of a sudden added an electron, it would be like handing you a feather on the scale. It's not going to change anything. All right, so now when we look at the atom and its size, all right, if we were to take one penny, you know pennies are made of copper, all right? Copper is an atom and an element on the periodic table. If we were to ask how many copper atoms are in a penny, all right, 2.4 times 10 to the 22 atoms. That is this many atoms, 24 with 21 zeros behind it. Atoms in a penny. So hundreds, thousands, millions, billions, trillions, quadrillions, quintillions, right? Huge number just in one small penny. All right, so just to give you an idea of what we're talking about with size, when we talk about AMUs and the mass and how large and small these atoms and their particles are. So let's take a quick look at a video just to put into reference how small an atom really is. All right, so what is this thing? Hopefully we all know it is the periodic table of elements. Periodic table of elements. Someone asked yesterday, well, what are all the different colors for? It's a really good question that we'll get into probably next class or the class after. And it just separates our elements and lets us know what they are. It tells us a little bit more about their properties right off, right? So the colors are just separating that for us. And so again, we'll talk about that as we move forward. So if we look at a block off of the periodic table, so let's zoom in here at neon. All right, and let's take a look at what that block at neon tells us. And you can look at yours in front of you on your periodic table. And so that number at the top is your atomic number. All right, very important that we understand our atomic number never changes. It stays with that atom. So think, you as a student may have a student number. All right. That number goes with the student. If you change the number, you have a different student, right? Same thing with atomic number. Every atom has an atom number. If I change the atom number, I now have a different atom, all right? So think about this. This is the social security number of an atom. This number right here is always going to tell us what atom it is. It tells us all the essential information we need to know about that atom, all right? Then you have your chemical symbol, which is just the abbreviation for your element, and then you have your chemical name. Some periodic tables will take a shortcut so that they can save some space and they don't write out the name for you, and you would just have the symbol. All right, but the one you have in front of you has your name and symbol while you're getting familiar with those atoms. And then at the bottom, this is your average atomic mass. It is not your mass number. It is the average. All right, so we're going to talk about mass number here in a second, but this is the average mass. All right, so I know that my mass comes from protons and neutrons, right? If we look back, came from protons and neutrons, and they both had a mass of what? 1. I don't see any decimals here, right? So how in the world did I get 20.18? All right, that's because some atoms of neon may have 11 neutrons and therefore contribute to a mass of 21, and others may only have 10 neutrons, and so it has a mass of 20. And so it basically averages out all of the neons known to existence, averages their mass together, and that's the number that's given to you on your periodic table. All right, so this is of all the neons that exist. If we were to look at it and look at their abundance, we would know the average atomic mass. So by this, I can say most of them, because my average is closer to 20, most all neons exist at a mass of 20. But there are some that are over that because, look, I have 20.18. So there's a few stragglers that change that average and throw it off a little bit. So let's take a little bit more into detail. Our average atomic mass is the average mass of all isotopes. And we're going to talk about isotopes tomorrow in detail. But that is the average of all atoms of neon. All right, any element that you look at on your periodic table, that mass number they give you at the bottom, which typically has a decimal, is an average mass. All right, very important that we understand this is average mass. All right, then you have your atomic number. Remember I said that's like your atom number that goes specifically with that atom. All right, that number tells us the number of protons. So if my atom number never changes, then what does that tell me about the number of protons? That is what identifies my element. Identifies element. And it never changes. If I change it, what does that mean? I've changed my element. I now have a new element that I'm talking about. That number of protons is specific to that atom. Again, think of it like your social security number. If I change your number, you now are a different person. So, number of protons. If I change the number of protons, you now have a different atomic number, and therefore, it's a different atom. All right, so atomic number never changes, and it equals your number of protons. All right, so there's your blank. And then you have 3 blanks that says blank equals blank that equals blank. It also equals electrons in a neutral atom. So I'll give you a second to write that down. Atomic number equals the number of protons, which also equals the number of electrons if it's neutral. All right, so what does this mean? So on the center of my atom, all right, you've got your protons and neutrons. If all I had was this nucleus right here, what is my charge? I'd only have 2 positives, right? So this would be a +2 nucleus. So then let's add some electrons. Now if I have the same number of electrons, I have a negative for every positive. So then they cancel out, and that's what makes it neutral. All right? For every positive, so I had 2 positives, I had a negative to cancel it out. All right, so for today, your protons and electrons are going to be the same. Those numbers are going to be equal. We are only dealing with neutral atoms today. All right, I'm not going to switch everything up on you. We need to focus on making sure you understand the particles before we switch anything up. So, number of protons equals the number of electrons today. That way we have a neutral atom. All right, so the atomic number is always known because we can find it right here on our periodic table. We will always know the number of protons that we have. It's never a guess, never a mystery. You always know the number of protons. All right, so in other words, those protons define the element. That's what tells us what our element is, how many protons it has. Those protons are so important, we gave them an atomic number based on the number of protons. That's how important your number of protons are. All right, so electrons and neutrons may change, and that's what we're going to look at next class. Electrons and neutrons, they can change. But, for instance, an example using carbon, carbon always has 6 protons. Always. If I were to change the number of protons, I no longer have carbon. If I all of a sudden had 7 protons, what would I have? I wouldn't have carbon. I would have nitrogen all of a sudden. Nitrogen, if you look on the top, has 7. All right? If I said, oh, wait, now I have 5 protons, not 6. 5, find your atom with the atom number of 5, and you will find boron. All right? So the protons define your element. That's what makes the element what it is. Let's take a look at mass number now. All right? Remember that mass number is not the same as the average mass. That is not what's given to you on the periodic table. This number that is given to you on the periodic table is an average of all neons in existence mass number. All right? So that means each individual neon may have a different mass number than the rest. So then you take an average of it, and that's what we put on the periodic table, because we want to represent neon as a whole and not just one specific atom of neon. When we're looking in the lab and when we're looking at chemistry, this unit, we're talking about mass number. That means the number that's specific to just that atom of neon. So imagine all of you in the room right now, you're neon. Each and every one of you. But you're also unique, right? You all have a different mass. So, if I took the average mass of everybody sitting in the classroom and I gave you that number, would that tell you the mass of the first person sitting in the first row? No, right? That is not the same mass as that specific person. It's that person's mass averaged into everybody else's. All right, so that's how you can think of the difference in, here's my average mass. This is everybody averaged together. But in my mass number, I'm looking at one specific person, one specific atom. All right, so that number is not found on the periodic table. Very important, it is not found on the periodic table. This is one that you're going to calculate, simple addition. All right, in order to know this number, it's either given or you know the number of neutrons. You will always either be given the mass number or the number of neutrons. You have to have it, all right? So how do we find mass number? Well, our mass is found by adding together the protons and the neutrons, all right? Remember, we always know protons, and so then we'll be given either mass or neutrons. Add them together, and you get the mass number. So if we have mass equals protons plus neutrons, which number do I always know for every atom? All right, it's the number that identifies what it is. Number of protons, right. So, oh, that was the wrong one. I meant to highlight it and not erase it. All right, number of protons is always known. So, if I'm given the neutrons, great. I can add it together and get mass. If I'm given the mass and I want to find neutrons, then let's just rearrange it algebraically. Subtract protons from both sides, and I get mass minus protons equals neutrons. Let's take a look at how we would show this and how we would abbreviate it out in nuclear notation. So you have a little spot in your notes so that you can label your example of nuclear notation. So first you'll see right here, and we've been looking at neon as our example all day. All right, neon is our chemical symbol. That tells us what atom we're talking about. All right, and then up in the top left-hand corner, you have your mass number. That is the mass number that is specific to this atom of neon. So for this atom of neon, it's 20. Remember, how do we find mass number? Protons plus neutrons. All right, for this case, 20 is given to us. We know our mass number already. Remember, we said we'll be given either the mass or the neutrons. And then at the bottom, you have your atomic number. That is always the same as the number of protons, and it's the same as the number of electrons if neutral. All right, and today, remember, we're only dealing with neutral atoms. So, mass number up top, atomic number at the bottom. Let's take a look at why is it written this way, all right? Or one way to remember how it's written. If you look on your periodic table in front of you or the one on the wall, you have your atomic number up top, and then NE and your average atomic mass on the bottom, all right? When we go to nuclear notation, all you're doing is flipping where they're at, all right? Flip it where it's at, and now you have the mass on the top and the atomic number on the bottom. Why the scientists decided that this was the way we were going to notate it, I don't know. But this is how, over the years, we've decided to notate. It's like, why do you decide to abbreviate your name the way you do? You just do, right? So same thing here. This is how we abbreviate it. This is the shorthand version so that you don't have to draw out that box on the periodic table anytime you're trying to talk about an element. So this is how we notate the mass and the protons in an element. Let's take a quick review of what we know from the numbers given to us in the periodic table in our nuclear notation. So we know that the atomic number is specific to that element. If you'll look through those 118 elements, they're all numbered in order, horizontally. All right, 1, 2, 3, 4, 5, 6, 7, 8, and so forth. All right, those atomic numbers that are going in increasing order tell us the number of protons, which define our element. All right, and if it's neutral, it also equals the number of electrons. And we're dealing with nothing but neutral elements today. All right, so if I want to then look at the mass number, remember, mass number is not the number on the periodic table. The periodic table is an average. This mass number here is talking about a specific atom, all right? So very specific. We're looking at the number of protons to that atom and the number of neutrons. Well, if I know the number of protons never changes, right? It's always consistent. I can't change the number of protons without changing the atom. So if I know that never changes, then what must change in order to change the mass number? My number of neutrons. All right? So today we're just looking at how that impacts mass as we change the number of neutrons. All right? As I said in the last slide, number of neutrons or mass will always be given. So we can rearrange it algebraically if I'm given the mass number and subtract our atomic number, our number of protons, and find our neutrons as a result. All right, the one consistency in this all is our atomic number. All right, now that we hopefully have a clear understanding of our protons, electrons, and mass number, let's take a look at some examples. These are in your packets there for you to do along with me. If we look at lithium, look at your periodic table in front of you, and what is the number of protons? Remember, number of protons is equal to the atomic number. All right, so the number in the top of your little box on the periodic table. So lithium is 3. We said that we're dealing with neutral atoms, so that means the number of positive particles and the number of negative particles have to be equal. So for today, protons and electrons are equal. Mass number. How do I find mass? Mass is protons plus neutrons. All right, so I have 3 protons, 4 neutrons, and that equals a mass number of 7. And so nuclear notation, remember we just talked about that. We've got our symbol, so Li, so how we abbreviate lithium. And then my atomic number goes at the bottom. Remember, it's flipped of what is on your periodic table. And your mass number goes up top. So 73 Li. Let's look at carbon. Atomic number for carbon, the number of protons is 6. All right, this time they gave me the number of neutrons again. So 6 plus 6 would give me protons plus neutrons, which is my mass of 12. All right, and then number of electrons, again, we're dealing with neutral atoms, so the amount of positivity and the amount of negativity have to be equal. All right, so that means I also have 6 electrons. Let's go ahead and write it out in nuclear notation here. We've got carbon with a mass of 12 and an atomic number of 6. Chlorine, atomic number of, hopefully everyone said, 17. All right, look, this time they didn't give us neutrons. So what does that mean? I have to have my mass. All right, mass minus protons gives me neutrons. So 35 minus 17 gives me my number of neutrons. So 35 minus 17 equals 18 neutrons. Looking at electrons, protons and electrons must be equal in order for it to be neutral. Neutral means it doesn't have a charge. All right? And so then let's write our nuclear notation for that. I've got chlorine, which is Cl, all right, an atomic number of 17 and a mass of 35. And then lastly, I've got silver. So look, here's where we use our nuclear notation. And it tells us all of this information in one nice little box, right? In one nice small spot, I can have all the information I need about an atom. So I can fill out all of these boxes from what it's given me down here. All right, we know the top number, 107, is my mass. All right, the bottom number, 47, is my number of protons, or my atomic number. All right. And so from that, I know that my number of electrons are going to be equal because we're dealing with neutral atoms. And then number of neutrons, we would take 107 minus 47. Look, it's written so that you can just do subtraction right there. 107 minus 47 equals 60. So then you have 60 neutrons. All right, so nice little, kind of see it as a puzzle to figure out. And so you've got one of those to practice with. Some of you may be asking, well, how do I know that it's neutral? How do I know that it doesn't have a charge? All right, if it had a charge, you would see something like +1 up here beside lithium, all right, or -1 beside chlorine. But because you don't see that, all of these are neutral. If you saw lithium +1, then you would know it was charged. Today, everything is neutral. All right, everything is neutral. So for today, electrons and protons are equal.